Here's a problem that the goal of it is sort of to mix the ideas of forces and kinematics. Kinematics, of course, just refers to straight motion, position, velocities, and acceleration. And it sort of goes like this. There's a tube here that has a bunch of compressed air in it, which is sort of contained in the tube here by some air compressor. And as long as this ball here that has this mass of 0.05 kilograms is inside the tube, the ball will have a 2 Newton force on. So sort of like an air gun. Just makes the ball go up, something like that. And of course, the tube is 1 meter long here, stated in the problem. So what the problem would like to know then is how high does this ball go up above the top of the tube once it's been launched. So once it goes all the way through, once it gets to this point right here, how far up will it go? So what you'd really like to know then is what is the speed of the ball? What is, say, the V naught of the ball right there? And if you knew that V naught, then you could apply the usual kinematics of something in free fall to see exactly how high it's going to go. But you sort of have to deal with all this launching business going down here. So what you can sort of get out of this problem here is that, well, it has a force acting on it. Okay, and so the force sort of implies that something's going to push on. In this case, is the air. And so how fast could this pushing possibly get the ball to go as it acts on it for the whole meter of the tube? The way you get something like that to work out is maybe to look at this equation 3 that we've used in class a few times now. The reason why I'm putting this one in here is because it involves this acceleration and the delta x, like the length of the tube is sort of built in there, so I figured that might be a good one to start with. And there's this a sitting here, which you might be able to use also. So it turns out that then if it starts at 0, this term starts at rest at the bottom of the tube. This is going to be 0 here. So the velocity squared, which it's going to leave with, is going to be something like 2. Now what are you going to put in for a? Well, we know then that one of the useful forms of Newton's law is that a is the sum of the y forces divided by m. And that'll be an ay also. So kind of the most general form of this equation here to use. Everything's along the y-axis. That's why I chose the y version of this. And indeed, I only do see one force acting on it. I just see that 2 Newton force on this thing. So if I process this equation a bit more now, I'll see then that a sub y is the sum of the y forces. All I see is the 1 2 Newton force. Here's a sub y. Here's that 1 2 Newton force. Then if I divide by the mass of the object right there, I can get the y acceleration, which this ball experiences while it's in the tube. That's what this Newton's law equation gives me right here. So I have something I can plug in for this a right here. And once again, it would be the 2 divided by 0.05. And how long is it in the tube? How long is this force act on? Well, over the course of 1 meter. So here's just sort of a fixed equation for you here, which you can then solve for. This is v. You can plug all that into your calculator here, and you can get some number for this speed here. Don't forget to take the square root. What is this speed? This speed here is the speed that the ball has as it leaves this tube. It is that launch speed. Now you can fall back on basic kinematics, and there's a variety of ways you can proceed with this. You can say, okay, if it has this v naught when it leaves the tube, and you want to know, for instance, how long is it going to take to reach its maximum height, you could say that 0, because everything comes at rest at its maximum vertical height, is equal to that v naught minus g times delta t. I'll sort of quit here. You can continue on where this v naught here was that v naught, the launch speed. And if you solve this for t, that'll be how much time goes by the time it reaches its maximum height. Then you can use another equation like y is equal to y0 plus dot 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 plus the 1/2 a delta t squared, equation 1, to figure out exactly what that maximum height would be. This would just be the basic kinematics. I think this is the new Newton's law stuff right here. Can you get that speed based on the force information given in the tube right there?